should.
That was
Yes, I heard.
No,
That's
no.
good.
Can you possess me?
I hope not.
I like you. Yeah, but the thing is that we have exchange, so all the people that work in different offices, they do every like two times a year we do this exchange. You from next door in the school, or is that the other offices do different offices they do things. So it's out there. Yes, yes. Some pictures and Instagram.
Emil, please. Welcome, everyone. We're going to close the doors, but there are still some people coming in. My name is Rui Costa. I'm Associate Director and CEO of the Zuckerman Mind, Brain, and Behavior Institute. And it's really my pleasure to welcome you, many of you, again, to this evening, to the Stavros Niarchos Foundation Brain Insight Lecture. So tonight's lecture series will be special. We'll talk about data for good, data science at Columbia. And Columbia is very lucky to have recruited Professor Jeannette to head this data science effort across the university. And I think we'll hear a lot. A lot of us are fearful of what data science can do, but a lot of us are also in awe of the new things that it allows, from health to society to humanity, and we're going to hear about this. Let me see. Better? Okay, I'll project. So, this wonderful lecture series is only possible through the generosity of the Stavros Niarchos Foundation, and we have here two representatives, and I would like to ask you, everyone, to thank them with me for their generosity. In addition to supporting these outreach and educational efforts with the lecture series, there's a special part, which is these lecture series are transformed in actual lectures then that are used by teachers to produce contents. And so we also have teachers here of around the community and students. And so it's really an incredible time at Columbia. We just opened not so long ago this new building dedicated to understanding what goes on in the brain. And of course, we are also all passionate about the brain. The brain is what makes us love and hate. It's what builds our personalities, what makes us decide, what makes us sometimes be nervous about making introductions to our new Data Science Institute director. But the amazing thing, if you think about it, is we're at a unique age, in a unique time in the history of humanity, where it could be that many of the kids born today will have life expectancies of well over 100 years. But no one wants to have a life that doesn't have a brain associated with it. So we don't want to live longer but not remember who we are, or what our relatives are, or what we like and don't like. So understanding the brain is important to understanding ourselves. It's also important to build a better society, not only health-wise, but in education. Now, today we're going to hear from Professor Wing about the mission of the Data Science Institute, and for society, for humanity in general, and how it impacts technology. But also we hear a lot about artificial intelligence, and you'll hear a bit about how artificial intelligence interacts with intelligence. And so the hope is that we can learn a lot from artificial intelligence that can help us preserve the life we like for all this time. And the hope is that this dialogue is bidirectional, and also, like some of our researchers do, use then brain-inspired architectures to try to influence data science and artificial intelligence. So it's really a pleasure to have Jeannette Wing here. she asked me not to be too long about introducing her, but I need to say a few things. She's a truly impressive scientist and person. She's a leader in the field. She got her degree and PhD from MIT, and then she went then to be in the leadership of the Computer and Information Science and Engineering at NSF. Then she was the head of the Computer Science Department at Carnegie Mellon, I think twice. And then she became the corporate vice president of Microsoft for 4 or 5 years. And then we were lucky enough to be able to attract her back to academia and to be the director here. Jeannette Wing's research interests are in areas of trustworthy computing, specification and verification, concurrent and distributed systems, programming languages, software engineering, and as you'll hear now, more AI networks. And as the head of the institute, she brings a lot of experience at Columbia, but most importantly, a vision for the future. And so today we're going to hear about that vision. She is a member of the National Academy of Arts and a fellow of the American Academy of Arts and Sciences and the American Association for Advancement of Science. And she is and has been in many of the committees that are debating everything that's going on. So when we fear what's going on, is someone worried about this? Is someone debating the evolutions? Yes, and we have such a person. So I'm going to be in complete awe trying to listen to the vision of Jeannette. And so thank you, Jeannette. Welcome. And let's hear about Data for Good.
Thank you. Thank you very much. I am honored to actually give this presentation tonight, and thank you everyone for coming. I am going to talk about Data for Good, data science at Columbia University, and I thought I would start by giving you a bigger picture of the data life cycle. The data life cycle starts with generating data, and there are many sources of generating data. We have large scientific instruments like large telescopes, neutrino detectors in the South Pole, the Large Hadron Collider, all of those very one-of expensive scientific instruments. They generate lots and lots of data. But the new kind of data that people are most interested in today is the data that's generated by people, the data that's generated by us. And someone else is collecting all that data about us and making lots of money off of that data about us. And that is part of the scary AI that people like to talk about. But in any case, people generate data, large instruments generate data, even the sensors and devices that are sprayed all around civil infrastructure generates lots and lots of data. So there's lots of sources of data, and that's just this first step. After you generate all this data, you collect the data. You don't always collect all the data you generate. And then you go on to process it. There's where usually there's compression, encryption, data cleaning, data wrangling, all those steps that you have to do before you even think about storing the data in some digital medium usually. But maybe tomorrow it'll be storing data on DNA storage. So storing the data. And you usually store the data in a way that you can retrieve the data quickly later. And that's what data management is all about. So when you look at how databases are architected, a lot of data management goes into that. Then there's analysis. And this is what is making data science so exciting today, because data analysis includes machine learning, data mining, and all those fancy techniques that people like to talk about today, like deep learning and reinforcement learning. So that's data analysis. And when people talk about data science, they sometimes just think about the data analysis. But I want you to think about data science more broadly. And then after you analyze the data, you're usually spitting out some numbers. So it's not good enough to give the end user a bunch of numbers. You actually want to give them some kind of visualization of those numbers, like a pie chart or a bar graph. But it wasn't until I joined Columbia and I talked to my friends in the journalism school, and this is the journalism school we're sitting in, that I came to appreciate the last stage, which I call interpretation, but what the journalists call storytelling. It's not enough to show pie charts and bar graphs. You actually have to explain to the end user, what am I seeing? What am I supposed to be getting out of this visualization? So when I talk about the data lifecycle, I really mean everything from the very beginning, generating the data, all the way to the very end, where a human being, or maybe a bot, has to take this interpreted data and do something. And throughout this entire data lifecycle, I care a lot about the privacy and ethical concerns of the generation, collection, analysis, and storytelling of all this data. It's one of the new areas in data science that I'm trying to promote in the Data Science Institute. So what is data science? I want to give you a very succinct definition of data science. Data science is the study of extracting value from data. And there are really two key words in this definition. One is value. And value is chosen specifically so that it is subject to the interpretation of the end user. So value to a scientist is discovery of new knowledge. And that's why we have those large scientific instruments that cost a lot of money collecting all that data, because maybe we will find a neutrino. But value to a businessman or woman is bottom line. And that's why you have all these companies that collect data about us and make a lot of money. And their value to a policymaker might be understanding sea level rise, to know when should I have my inhabitants start moving their houses from away from the coastline. So policymakers can gain a lot of value from data as well. And the second word that's important in this definition is extracting. So it takes a lot of work to get that value, all that work in that data life cycle, and so let's not forget that. So I have a three-part mission statement for the Data Science Institute at Columbia University. The first is to advance the state of the art in data science, and this is about pushing the frontiers of basic research. It's about advancing all the aspects of the data life cycle I showed you, and it is about discovering new knowledge. The second speaks to the full-fledged nature of Columbia University, which is to transform all fields, professions, and sectors through the application of data science. And indeed, the entire university has really recognized the importance of data in their research and education. Many of the faculty and the chairs and the deans have come to me and said, I really need your help. I have this really interesting data set, but I don't have any data science expertise. So it's a good position to be in when you're in high demand. And finally, ensure the responsible use of data to benefit society. And to benefit society means using data to tackle those societal grand challenges like healthcare, energy, climate change, social justice. And ensure the responsible use of data is really making sure that we pay attention to the privacy and ethical concerns as we collect data about people and as we analyze this data and tell people about their behavior or use that data in other ways. So to summarize my three-part mission statement, I like to use this three-word tagline: data for good. So just remember that from my talk, just remember data for good, Columbia University, okay? Data to do good, and using data in a good manner. We really are university-wide as well as university level. We have over 300 affiliated faculty from every single school on campus, from architecture, arts and sciences, business, dentistry, engineering, international and public affairs, journalism, law, medicine, nursing, public health, and social work. And since I got here, I have also reached out to Barnard College and Teachers College. So we are truly university-wide. And every school, every college, they're all participating in the Data Science Institute. We have a robust industry affiliates program. At any point in time, we have about 25 companies who are industry affiliates. Industry affiliates have the benefit of working directly with our master's students on a capstone course. They get to bring in real-world data, work with a team of students who actually light up their data. And you can see we represent some international companies there, like Alibaba and Baidu and Didi. And we have Neoway from Brazil. So I want to go through a few stories using my mission statement as my index. Normally, at this point, I would tell you about some of the most advanced research that's happening on campus in terms of data science. But I was warned that this is a very broad audience, and so I thought for this section of my talk, rather than tell you about some fancy schmancy expectation maximization algorithm, I would actually share with you what I think is the state of the art in data science. And why is there so much interest in data science now? And the short answer is AI, artificial intelligence. So the way I like to think of it is data science and artificial intelligence overlap. One is not part of the other, they overlap. And what's in their intersection are many things, but one key area that's in their intersection is a subfield called machine learning. And it is because of big data that we are seeing the successes of AI. And I'm going to get to one of the most profound successes in a second. So today's successes in AI are due to the large amounts of data that we are generating, that scientific instruments are generating, that we're all generating. So what is AI anyway? And I always like to go back to the founders of AI when they had a conference at Dartmouth in 1956. And that was really the founding of the field AI. And I quote here from the proposal they sent to the government to get funding for that conference, because in that proposal they basically say, we are thinking about building a machine that can simulate the intelligence of humans. And that basically defined what artificial intelligence has meant to be. And very early on, even at the Dartmouth conference, these grandfathers of AI recognized that the vision they had for building a machine that could simulate human intelligence was too grandiose a goal. And for those of you who follow the media and the literature in this, that's currently called AGI, artificial general intelligence. And we're not close to that yet. What the people in 1956 realized is that humans are so intelligent that maybe what we could better do is break down human activity into separate tasks like speech and language and vision and motion, like walking. And maybe we can make a human simulate that task, like vision and speech and so on. So what spawned out of AI were all these subfields of computer vision and computer speech and machine translation and natural language processing and robotics. All of those ended up being their own fields within artificial intelligence. And they all went off their merry way. So that is what AI is. And now the question is, can machines really learn human behavior? And what we found was, I'd say around 2000, late 90s, early 2000s, all these separate fields of AI started using this technique called machine learning. The computer vision people stopped trying to actually understand the semantics of an image, but just used machine learning through machine learning at understanding what was in the image. And similarly with speech and natural language processing and so on. So now all these separate fields of AI started using a common technique. And that's what really elevated progress in each of the separate fields and brought everyone together saying, hey, there's something going on here. Maybe we can actually think about building a machine that can be as intelligent as a human. So how do machines learn? What can we really do today? So in the middle, I put this computational model. That's just the computer. It could be an algorithm, it could be a piece of software, or just piece of hardware, but that's your computational model. And if you feed it lots and lots of data, say about people, what this model can do is make a recommendation, like what movie would you like to watch? That's why you get certain recommendations from Netflix, whereas your neighbor might get different recommendations. What kind of picture, what kind of object is in that picture? Is it a cat or is it a dog? That's a classification problem. Or it might make a prediction. What are you going to type next? So there's some keyboards that actually predict the word you're typing, or the next word you're going to type. That's all using machine learning. And the idea is we train a model with lots and lots of data so that on a single person, we can make a recommendation. We can classify that person's preferences, or we can make a prediction about that person. And that ends up personalizing these computational models. So that's me. Okay. So let me give you an example. This is a very old example, but the example is, suppose I have a lot of pictures. Some of them are easily, we could recognize as faces, and others are not faces. And the machine learning problem is to find the line that separates the faces from the non-faces. And mathematically, that means find a function that can distinguish between a face and a non-face. And if I just abstract this a little bit with dots, blue dots and red dots, I'm trying to find a separator between the red dots and the blue dots, the faces and the non-faces. Now in reality, the dots are not so well behaved. And the idea then is if I have a new dot that comes along and I have this separator, I will easily know, oh, it's a blue dot or a red dot. In reality, the dots are not so well behaved. They look a little jumbled up, and my separator is not a clean straight line, and I might actually get some of the dots misclassified. But in machine learning, that's okay. It's good enough to have a function that basically does well enough. And it gives you an approximation with high probability. If you give me a new dot, I can give you the right classification. Now, this is just red dots and blue dots in 2 dimensions. In reality, we have many dimensions, say n dimensions. And so what we're really learning, trying to learn, is a hyperplane for n dimensions. So this gets really complicated when you can have hundreds or thousands of features in any one object that you're looking to classify. But we can do it. That's what's so amazing about current technology. So in particular, there was a huge breakthrough in 2012, not too long ago. And it was a huge success in AI. And it happens to be very remotely related to neuroscience, so relevant for today's lecture. So what was the 2012 breakthrough? A success in AI, and how is it related to neuroscience? The answer is deep learning. It also goes under the name deep neural networks. And let me explain how it all fits in. So remember, I told you already that data science and artificial intelligence overlap, and in the intersection is this general area of machine learning. Well, inspired by how the brain is wired, deep neural networks are architected to be sort of like how the brain is wired. And that is why I draw a dotted line for the neuroscience part of this Venn diagram. Neural networks were inspired by the brain, but it's just a metaphor. So don't take it too seriously. Although I continue to be astonished by the successes of deep learning. And where does it fit in? Well, it fits right there in the middle. It's a kind of machine learning technique inspired by the brain. And this is such a profound achievement that just this year, the 3 people who founded deep learning, Yasha Bengio, Jeff Hinton, and Yann LeCun, won the 2019 ACM Turing Award, which is considered the Nobel Prize of computing. So this is really quite a recognition to these 3 people. And I wanted to just make a side remark that I knew Jeff Hinton when we were both at Carnegie Mellon together. I was a junior faculty and he was a bit more senior. But I remember he used to talk about these neural networks inspired by the brain and how, you know, he was going to build a computer that was going to look like the brain. And this is back in the 80s. And all of us kind of smiled. We really thought, well, you know, people can work on whatever they want. That's the beauty of academia. But he kept plugging at it. And others came along after. Yann LeCun did a lot of his best work in deep learning when he was at Bell Labs. And Yasha Bengio worked with him there. And so these people are still doing great work and really true heroes to AI and machine learning and computer science. So how does a deep neural network look, and how do you build this function that's supposed to do some kind of classification or prediction? So let's suppose I want to build a classifier for cat images. So the way you do this is you have to feed in a lot of images of cats, and they're all labeled cat, 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 and you feed this into this architecture, which is really just layers of neurons. The black dots are neurons. They're just nodes, but they're called neurons. And the edges are like synapses, but really they're just edges. And the outputs from one layer are the inputs to the next. And these nodes are actually computing sophisticated functions. They're nonlinear functions usually. And what is traversing on the edges are weights. They're usually real value numbers. So at the very end, after you feed in all these cat images, you have some numbers on all the edges, such that if I feed in a new image that it hasn't seen before, and it's a cat, it will with high probability say it's a cat. And I feed it a different image, and with high probability it will say it's not a cat. So that is the bottom line of what deep neural networks are. But what is so amazing is that this one idea has shown applicability everywhere. So this is just back to faces. This shows you a kind of neural network that has a little more structure. It recognizes faces. And I wanted to show you a little bit of the insides that you can see as you go further towards the output layers. There's actually more information about the face that the network is learning. So by this layer, you're actually seeing some features of the face. And then by the end layer, you're actually recognizing faces. And this is true of any neural network that you're training. Somehow, by magic, as it goes through all these layers, it's learning more and more about the images you're feeding in. And neural networks are used not just for images, but it's used for speech and machine translation and all sorts of things. So the state of the art, to summarize in terms of where we are in deep learning, is that face recognition is basically a solved problem. And I remember when I was at Microsoft in 2014, we were sitting around a dinner table. In 2014, that was only 5 years ago, we're sitting around a dinner table saying, where do you think AI will be in 5 years? And these are all AI experts. And my boss, who was a computer vision expert, said, I think we're going to solve face recognition in 5 years. And we all looked at him saying, wow, that's really a bold statement. But it happened in less than 5 years from 2014. And so things moved really quickly. Speech recognition. If anyone has an Alexa on their kitchen table, it's got deep neural networks in there recognizing your speech. Machine translation. So translating between two different languages, deep neural networks are helping you do that. So if you use Skype Translator, if you go to Google Translate, every time you get a letter in a different language from a loved one, you could just type that in. That's deep learning behind the scenes. All these vision systems that deep neural networks are good for, they are in your self-driving cars. And they are in your Tesla, if you happen to have a Tesla. So this is real stuff now. It's not experimental. It's not in the lab. It's in your home. And I think what really moved the needle was when deep learning and reinforcement learning, the combination of those two techniques, were used in the machine that beat the human Go player. Not only did that make a lot of press, but I think that was a nudge for China to really move big in AI. So that's state of the art. In terms of AI and medical imaging, not just deep learning, there are many, many startup companies in this space. And there's still some interesting research projects going on. There's a contrast depending on who you talk to. There was a survey sent to many computer scientists recently from radiologists at Stanford. And they wanted to know, basically the survey expressed some anxiety on their part on whether their jobs were going to be taken over by machines. And they were asking us computer scientists. So there's some anxiety already in the medical community about whether with this AI computer visioning capability, whether people like radiologists and so on, I wouldn't say whether their jobs will be replaced, but whether their jobs certainly will be enhanced by these techniques. On the other hand, I have a friend who's a pathologist, and she doesn't believe in any of this. So you get these different reactions. Okay, transform all fields, professions, and sectors through the application of data science. And here I'd like to breeze through a little bit and share with you some of the exciting research going on here at Columbia University in different fields where they are using AI, machine learning, deep learning, data science, and so on. This is beyond just deep learning. It's really about how different fields are using data science. I will, however, start with neural networks, and I deliberately chose this example because it intersects with neuroscience. So this is really hot off the press, March 2019, a paper that was presented by some colleagues of mine on neuroscience and deep learning. And as you know, there are two main ways in which we take images of the brain. One is through EEGs, where we get very good temporal resolution of a few points on our brain. And the other is fMRI scans, where we get whole scans of our brain, good spatial resolution. And their question is, why can't we use both to maybe get more information? But before getting to that, they wanted to see if they could build a model, and they built what are called convolutional neural networks for one kind of data to see if it could predict the other kind of data, and vice versa. And so they built two convolutional neural networks, one as a transcoder between EEG and fMRI data, and the other way, and got good results. But this was all on simulated data. It's a nice first step, though. Another example from the biology world, this has nothing to do with deep learning, just a lot of data, was understanding the tumor microbiome to combat cancer. So this group of authors looked at the bacteria, the microbiome around pancreatic tumor cancer cells, and they discovered that the microbiome was counteracting the effect of the chemotherapy treatment. Not very good. Like, that makes your chemotherapy completely ineffective. And they used the genetic sequencing of the microbiome, the bacteria, to discover this. But they went one step further, and they saw that if you injected the tumor cells with an antibiotic, then the antibiotic would counteract the effect of the microbiome, therefore making the chemotherapy treatment effective. So it's a good story in the end. This is all on mice, however, all on mice, so they still have a ways to go. But it was already an interesting discovery. Another science story comes from my colleagues in the astronomy department. They, as many astronomers, look at lots and lots of images of the sky from those large expensive telescopes. And what they do is, what they and others are trying to do is understand the Big Bang model. And what they showed, again, interestingly, using convolutional neural networks, they showed that using these convolutional neural networks, they were able to better estimate the parameters of the Big Bang model than off-the-shelf traditional statistical techniques. So this is one of these, wow, that's great. And then the question is, yeah, I wish we could really understand how deep learning really works. But this was first on simulation data, and now they're going to do it on real data. In a completely different sector, I have colleagues in financial engineering and in business who use machine learning, and specifically in this case reinforcement learning, in this whole area called robo-advising. So if you're lucky enough to be wealthy and you have a personal advisor, you usually interact with your personal advisor every few months, and over time your personal advisor learns your preferences. You know, do you like to put all your money in the stock market, or do you like to put all your money under your mattress, or somewhere in between? But it takes time to learn one's preferences, and as the market changes, of course, your preferences change. What this group of people did is to automate that using this technique called reinforcement learning, to basically automatically learn your preferences for investment. And they basically found through a very short number of iterations of the algorithm, they could learn your preferences, you know, in minutes as opposed to months or years. This work is so new that the authors are still looking for a Citibank or JP Morgan or a Chase to give them data so they can test out their techniques. Now for something completely different. We have what I like to think of as a very modern history department, history faculty who are well versed in machine learning and other kinds of AI and data science techniques. In this particular case, they use a technique called topic modeling to scan all the documents that they've accumulated and to look for interesting events. So this history department, Matt Connolly in particular, has amassed the largest set of declassified documents. So as you know, the United States government every year declassifies a set of documents. And what they've done is they snarf them all up and they put them in one repository. In this particular example, they looked at cablegrams sent between diplomats in the 1970s. And they looked at all the contents of the cablegrams, the to and the from and the subject fields, and they basically did word analysis on the cablegrams and topic modeling to discover what they called unusual events, thinking that an unusual event might align with a real historical event. And sure enough, they looked at all these cablegrams in the 1970s, and every black dot represents an unusual event. So you'll recognize some of them: the evacuation of Saigon, the death of Mao Zedong, and so on. So we have a lot of breadth of use of data science at Columbia. Now what I wanted to focus on is the last part of my mission statement, which is data for good, responsible use of data. And I like to talk about responsible use of data in terms of this 5-letter acronym. I'm not too happy with this. An acronym that's more than 3 or 4 letters is not a good acronym. But it lets me remember the things I need to talk about. So fairness, accountability, transparency, and ethics. These are the words that you hear and read about a lot. You've been reading a lot, for instance, in the news about biased algorithms, or should I more accurately say biased data that's fed into algorithms. then create biased models. Accountability, transparency, ethics, safety and reliability, security and privacy. That's the one story I want to share with you. And it goes back to the computer vision system I mentioned before. So as I mentioned, these deep learning-based computer vision systems are in your cars, are in your self-driving cars or your Teslas, and maybe some more advanced luxury cars. What this group of researchers did is they showed how you can take an image that's classified in one way and just systematically modify that image to make it get classified the wrong way. So what this image is of a road turning, curving to the left with a guardrail there. And if you imagine driving the car, you want your car to make sure that you veer to the left. But by just darkening this image, the car, the self-driving car, will think, oh, veer to the right. And then you hit the guardrail, fall off the cliff, and die. And that's why they detect fatal flaws. And they found thousands of such vulnerabilities in state-of-the-art vision systems based on deep learning. So that's not good. And that's why there's reason to be concerned. The good news is that we have researchers who are trying to understand where things are going wrong, or at least come up with tools and testing techniques to make sure that what systems are deployed are safer and more secure. Okay, what about tackling societal grand challenges? And here I really have great colleagues working on really hard problems. So let me start with social justice. We have a great collaboration between faculty in the social work school and in our computer science department who have been studying they've been studying the tweets that Chicago gang members send each other. And the idea is, the idea is this. If you can understand through the tweets that people are sending each other that people are feeling aggressive, then maybe that's a good time to intervene, maybe through a social worker or law enforcement. It turned out that this language with which the Chicago gang members talk to each other in tweets is its own language. There was no other language that looked like that, so we had a natural language processing expert in our computer science department come in and help basically parse the language, figure out a grammar for the language. A lot of the words are emoticons or images or abbreviations, and they basically did a parts of speech analysis of this gang language. And they were able to build a classifier for these tweets that can determine whether the tweet is expressing a feeling of loss or a feeling of aggression. Whole other topic is climate science. Of course, Columbia University has the world's experts in climate science with the Earth Institute and Lamont Doherty. And this particular project is a software project that is providing an open source platform for climate modelers to put their data, their models, their algorithms, the results all on one platform so everyone can share their results. And they're using this already to do prediction in hydrology, meteorology, and all sorts of other aspects of climate science. One video I would like to play for you is a simulation of the ocean currents on Earth. This is really just a big data problem. This is simulating 2 petabytes of data. And it's predicted this year or next by the Intergovernmental Panel on Climate Change, IPCC, that we will have 100 petabytes of data ready to be simulated on our supercomputers. Just to contrast, my understanding is the human brain can store up to about 2.5 petabytes of data. So we're talking about 100 petabytes of data coming fast and furious that our climate scientists are going to relish in needing to simulate. My last story on data to do good is in healthcare and big data. So Columbia University is the coordinating center for this huge international project called Odyssey. It stands for Observational Health Data Sciences and Informatics. Its goal is to have 1 billion patient records. Currently, it has 600 million patient records. 600 million. So remember, the population of the US is much less than 600 million. There are 25 different countries. Over 80 databases are accessed through this federated project. And I wanted to share with you a couple of results, observational and research results that they were able to tell by looking at just the data. So these are 600 million electronic health records. So for those of you who are in IT, and I know at least one of you in the audience is, this means these 25 countries, these 80 clinics that are sharing their data with each other, had to agree on a standard. And they did. So that is, when you can do that, represents one of those 80 data sets in the federated data set. I'm only, for each of the diseases here, I'm only showing you 3. So for instance, the topmost on hypertension, CUMC, is Columbia University Medical Center. So if you ever went to Columbia University Medical Center for hypertension, you're in that data set. And what they discovered is, so the way to read this ring of circles is, for the disease that you might be diagnosed with, there's a line of treatment, a series of drugs that you're given to treat you for that disease. So they start you out with one drug. So let's say that's the inner circle, the chartreuse colored drug. If that works, then fine. But if that doesn't work, they give you a second drug. And that represents the second ring. So that might be some drug that's represented by the color red. If that works, then fine. If that doesn't work, they give you a third drug, and so on and so forth. So that's why you have each radius in that circle is a single patient. And you can see that some patients take maybe 3 or 4 drugs before they get better. So what they found is, for hypertension, if you collapse, and I'm not showing you the collapse here, if you collapse all of the records that they used for this study, and they used 250 million records for this, they showed that, this is around the world now, they showed that 1/4 of the patients in that data set are treated uniquely. 1/4. That is amazing for hypertension. You would think there's kind of a standard treatment, everyone gets it, and it works. So that was not something you do a clinical trial on and discover. That you only discover by looking at the data. And then you start asking questions. So let me give you one more story about this, since I went through all this trouble to tell you how to read these rings. This is the diabetes column. And for the most part, all the rings of circle look like the top two. In other words, that chartreuse drug does a good job for most people. This one down below was the outlier. And this one comes from a Japanese medical center. And it turns out, by looking at this, the researchers discovered that the Japanese are genetically disposed against that chartreuse drug. So that's why you can see it didn't work for many of the Japanese. They had to take 4 or 5 other drugs, or the doctors knew not to even prescribe it. That was also discovered by looking at the data. And now they're trying to understand why. And of course, I asked my colleague, George Ripsack, who was behind this study and the coordinator for Columbia, I said, well, what about the Chinese and the Koreans? And he said, no, that it was only for the Japanese. So it's really interesting. I don't know why, but that's for the medical scientists to figure out. Okay, so now, in my last few minutes, I trying to relate to the neuroscience part of this lecture. I wanted to just close with some speculation about the future. What's ahead for data science, AI, and neuroscience? And obviously, part of my answer is that there are many opportunities in neuroscience using data science and AI that are yet to be explored. At the same time, there are many challenges in data science and AI that continue to hold. But what I thought would be interesting to explore is this bilateral relationship between neuroscience and AI. So remember what I said, that deep neural networks were inspired by the brain. At the same time, what has happened is, of course, neuroscientists are using deep learning and other fancy machine learning techniques to actually discover new science about the brain, and that's wonderful. So now maybe it's time for us to see, let's look at the human brain circuitry a little more in detail and add some of the complexity that the human brain really has to this simplified deep neural network. And this is not my idea, but I think it's a great idea. It was written in an article just published, and he proposes a few research questions, which I wanted to share with you. First of all, the neuron itself in my diagram is just a simple node. There's a function that it computes based on the input edges from the left, and it spits out some output on the right. But neurons in the brain are much more complicated. They have they're different types, they have different structures, and maybe there's something that we could do to add some more complexity to our deep neural networks in terms of adding more complexity to our neurons. That's one thing. The other is the connectivity. Again, the deep neural networks are very hierarchical. They basically go from left to right. In some networks, you see some loops, and those are recurrent neural networks. But in our brain, connectivity is much richer and more complicated than this kind of simple hierarchical connectivity. And then there are deeper questions like, what aspects of biological circuitry are computationally essential? That seems like a profound, perhaps philosophical question. But as a computer scientist, I always like to think about computational complexity and what problems can and cannot be solved by computers. And then finally, what are human learning tasks that elude DNNs? And here I go back to AI and its roots, and that the advanced artificial general intelligence, the dream of building a machine that can be as intelligent as a human. And I think about how babies and children learn, and how we don't know how they learn. We can't even come close to building a machine that can learn as well, as much, however babies and children learn. And so there's some things we can do really well. They drive our cars. But some things we still don't understand. And by the way, babies do not need to be fed thousands and thousands of pictures before they can learn what a cat is. So there's still something we don't understand. With that, thank you very much.
Time for some questions. Please use the microphone there. Take your time.
I know there are high school students back there dying to ask me questions.
When I was an undergraduate here at the engineering school, I never heard any talk about ethics. So when my son went to MIT and took course 6, I said to him, please look into ethics courses. I'm surprised in this day and age, especially in light of what's going on with Facebook and some of the things that you mentioned, that it's not a required course for every undergraduate student. Can you tell us what Columbia has planned going forward?
It's an excellent question, and it concerns me as much as you, and I'm glad you brought it up. When I first got to Columbia, I asked where's the data ethics part of the data science master's program, and it's part of the capstone course, but to me it was insufficient. And that was before Facebook and Cambridge Analytica and the Russian hacking of our elections. It was just me being who I am. But since then, because now Zuckerberg had to testify in front of Congress and blah, 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 data ethics has been really come to the fore for data science and computer science. The computer science department at Columbia does offer a data ethics course, and the engineering school does offer professional development a week or two where data ethics in engineering is covered. But I think especially for data, it's important to kind of really emphasize it more. I was just at a retreat with the computer science department, and we talked a lot about not just making it a course that's optional, but how to inculcate ethics in the entire computer science curriculum. So some of my colleagues just got a grant from the Mozilla Foundation to do exactly that. So we have 3 faculty who have volunteered for their courses to be guinea pigs, and we'll see how that goes. So there's action being taken here at Columbia University in this space.
Thank you.
Just as a follow-up to that question, I wonder if you'd address the imbuing of ethics and morality in the machines. And I use as an example the self-driving car, and maybe trite example, which I'm a journalist, I've covered car tech. And so I've been discussing with people in certain interviews on occasion the idea that the car will have to decide whether it hits a bus and kills the passengers or swerves and kills a kid on a bicycle. Can you address that?
Yes, this is commonly known in the ethics community as the trolley car problem. So this is an old ethical question where the trolley car switch operator has to decide. There are 2 tracks, that the trolley car is coming down, and there's 2 tracks. On one track, there's one a man tied down, and the other track there's like 3 boys tied down, and the switchman has to make the decision, do I kill this one person or these 3 people? And in ethics, you don't actually have to solve this problem. You just philosophize about it. But now it's a real problem, and it's a real problem because some algorithm or some piece of software is going to have to make that decision. And let me get to my answer in a second, but I wanted to say that the DSI has a seed grants awards program, and we gave a seed grant award last year to a project that is looking at how to negotiate both human-driven cars with autonomous cars on the road at the same time. And they specifically wanted to address the ethical issues. So they brought in a faculty member from the law school to help them think about the ethical issues. He has since really glommed onto this problem and just published a law review article on the kinds of questions you're asking. There's a very cold way to think about how this problem may eventually get solved. And that is, you do a calculation, which means someone is weighing something against something else. And then there are external entities like insurance companies and lawyers and whatnot, regulators, to police and monitor the situation. I don't have any answer to the trolley car problem, but I think it's tip of the iceberg. Speaking of MIT, MIT put out a little test your ethics on this very problem. They had, I don't know, 20, 30 different scenarios of the trolley car problem, and you're supposed to answer that or that, and you can see it's very uncomfortable after the first five scenarios. So I don't know how the car companies right now are thinking about it. I don't know what decisions they're making, but it's a good question because it's not rhetorical anymore.
So my context, my question is based on the fact that I entered a competition here at Columbia, which was titled The Use of Blockchain in Clinical Trial Recruitment and Trial Management, with addressing the feasibility of a cryptocurrency to help increase that. What are your views on collecting data in the healthcare industry, in particular like clinical trials and clinical management, which could expand the side effects to individuals, which could include like suicidal behavior, harm to others, or create other side effects? How do you think data should be used in the healthcare system, specifically that, and what ethical and moral aspects should people consider when implementing like blockchain in certain sectors? Because there's also different things to consider, like the exchange of information between different hospitals, and like you gave the example of like the different hospitals and how much information the patient can know themselves about the internal data that's getting exchanged.
Okay, let me, you asked a lot of questions in that statement. Let me answer a couple of them.
So I guess, oh, sorry. So I guess the first one would be, how should people consider exchanging data in between systems, in particular the healthcare system, with consideration to their patient?
Okay, let me answer that question. So I actually do research in privacy. And believe it or not, there are what I call privacy-preserving technologies that have mathematically provable guarantees that can allow two entities to share data in a manner where both entities can benefit from the pool data, and neither entity can see the others. The techniques are based on cryptography, not the blockchain stuff. Some of these techniques have been around since 1982. These were seemingly theoretical techniques, but now they have come into practice. They are being used to solve point solutions for point problems, and they scale for the point solutions. I'm thinking about specifically techniques like secure multi-party computation for any of those who might know about that. A more recent technique that was invented by, or solved, it was a problem that was outstanding and solved by Craig Gentry in 2009 in his PhD thesis. He's now at IBM, is a different cryptographic-based technique called homomorphic encryption. And this is where you can store data on one site, and some other person or some other site can actually perform computations on the encrypted value of the data, and neither the host of this data can never see your query or the results of the query. So that's homomorphic encryption. It is also being used for point problems with point solutions. And finally, there's a technique called differential privacy, which has gotten the news recently because Census 2020 is talking about using it. This is not a cryptographic-based technique. It's more statistical in nature, where you're adding noise to the output before you actually give the final result to the end user. What I'm really trying to say is that there are technologies that can come to play to light up the scenarios you're talking about, to ensure the privacy of the data sets that, say, hospitals have, or data about patients. So that gives me a little hope that you know, what you're concerned about can be addressed from a technological point of view. There is already a lot of regulation that keeps hospitals, clinics, researchers in check in the healthcare space. And that's really a good thing. The first person who asked me a question was really remarking that unlike in medicine, law, journalism, and business, where you're trained as a professional with ethics in mind, unlike those fields, in engineering and science and now data science, we haven't made it a requirement. So I think that's where the emphasis has to happen. At the same time, I speak to the dean of the public health school. She oversees the biostatistics department here at Columbia University, and she is recognizing the new ethical issues being raised because of the collection of data about people in ways that people may not even know about. So I think you're raising a very good question, and we are still in the midst of solving it.
What are your views on using data collection and different systems like blockchain technology to collect patient information for clinical trials and clinical management? Do you have any ethical insights about that? I think more generally, I'm not sure blockchain is relevant to your question at all. It's just a technology. Yeah. So I think it's a red herring in your question. I think the question is, what are my views on collecting health data about people? And the general rule of thumb is that if people volunteer their data, usually for the good of science or for the good of research, I think that's great. If people are not opting in or giving their data for the good of science or research,
then I think there's a question of why are you collecting this data? What are you going to use it for?
Thank you. I pose that question because, say, some network included insurance companies, and America doesn't have universal health care. So depending if insurance company has had access to their blockchain technology, like the patient files, blockchain technology, you can't really tamper with it, and it's encrypted. So it would probably influence how certain patients are insured depending on if insurance companies had access to that technology and data. So that was just my concern about ethical perspectives. But thank you.
Question?
Hi, I wanted to know that Odyssey database. How did so many institutions, or how did you or whoever organized that, or enlist so many institutions, medical organizations, to participate in that?
You would have to ask my colleague George Ripsack. I think it's pretty amazing.
It is amazing.
Which is why I wanted to share this pretty amazing Columbia story with you. George Ripsack is the chair of the Biomedical Informatics Department at the Columbia University Medical Center. And he, I think he has daily, but certainly weekly phone calls with the 80 participating organizations, and they just are on top of things. It takes very coordinated effort, but people see value out of that.
Yeah, I'm at IBM, and I was just curious as that how.
I'd be happy to link you two together.
Okay.
I don't. Would IBM want to contribute? I don't know, but
We'll
in
talk
any
afterwards.
Case, yeah.
Thank you.
Mark, please. Yes.
This is asking you to speculate. Do you think there will ever come a time in areas like medicine, climate science, and so on, that there will be enough data to be able to talk about not probabilities but certainties? In other words, can you get beyond informed speculation?
I suspect not, because if you think about nature, this is now not being not speculative, but being philosophical. If I think about nature, nature is unpredictable. There's inherent randomness, and we're always going to have to deal with uncertainty. If you think about human beings, so many of my friends who are in robotics tear their hair out because those poor little robots have to interact in a completely unpredictable environment. Like a human being will step in its way. And that's what makes building robots so difficult. And that's even in a controlled environment. You can never know what's going to happen. And so that's in a controlled environment. And then you think about Mother Nature, and she's maybe deliberately unpredictable.
That's precisely why I asked the question.
But isn't it better to have life as non-deterministic rather than deterministic?
Indeed, I would. Yes.
All right. Well, we're ending on a philosophical note.
That's fantastic.
All right.
So I just wanted to thank Jeannette for this absolutely fabulous lecture. I hope this stimulates your brains. Again, we thank the Stavros Niarchos Foundation for the amazing support for making this possible. And if you want to get engaged with supporting neuroscience or supporting data science at Columbia, please talk to us. I hope to see you at our next event in the fall. Thank you so much. Good evening.